story of science, changing man's way of life in our time. Men have always yearned and tried to fly. Some of the earliest motion pictures ever made recorded mechanical birds and other efforts of 19th century inventors. An early dragonfly shape designed by America's Samuel P. Langley resembles those later flown by pioneers George Cayley of England, Santos Dumont of Brazil, and Henry Deutsch of France. The experiments of the Wright brothers at Kitty Hawk, North Carolina, were another step into the sky, the first of 1,000 needed to attain useful practical flights. In the years and decades that followed, new records for speed, altitude, and distance were constantly set. Yet until very recently, the priorities of aviation science have remained unchanged. Faster, larger, longer-ranging, higher-performance aircraft. Only in the 1970s have growing problems, spiraling costs, crowded skies, the need for greater efficiency of men and machines, led to new and revised priorities for aviation researchers. Today's wind tunnels, for example, are being applied in the search for safer, fuel-saving, high-performance designs. In the test section, sensors measure the model's responses to stresses. In an arid lake bed in the Mojave Desert of California, another model is being tested, a scissors-like design called the oblique wing. This 7-meter model employs ideas that may someday allow full-scale passenger jets to fly faster than the speed of sound without producing a sonic boom, as well as make large have been completed for a full-scale oblique wing transport. The wing would return to a normal angle for takeoff. Better aircraft components are being sought. Here, a new, strong, lightweight composite material, a blend of metal and plastics, is being used to fabricate an experimental wing. Using composite materials rather than metal alone can decrease aircraft weight, reducing fuel consumption. Such materials are now undergoing flight. Even aircraft tires are being improved. Keeping modern aircraft in tires is a definite economic problem, since the lifetime of a tire tread can be as short as 10 takeoff landing cycles, depending on the airplane and its operations. Unlike automobile tires, aircraft tires are retreaded 5 or 6 times before being scrapped, mainly because the tire body does not deteriorate as quickly as the tread surface. Several years ago, the United States Aeronautics and Space Agency began developing a new synthetic rubber calculated to increase the strength and durability of aircraft tires. The new rubber compound combines strength and longevity, key qualities for airplane wheels. The testing program for the tires included evaluations on a landing load track, which exposes tires to braking on both dry and flooded concrete runway surfaces. After further experiments, the now fully certified polymer tires are coming into active use. To date, the new compound's wear performance remains superior to that of conventional tires. Perhaps they may eventually be applied to cars and other vehicles as well. One focus of modern flight research is the link between flyer and aircraft. A current project aimed at making this relationship more efficient employs a television camera scanning a model runway from which a computer abstracts the key landing data. The key information is then presented on an electronic display. Many of today's studies are aimed at improving such man-machine systems. In general, one can easily design systems which respond well under ordinary conditions. But can these systems be made to perform usefully in an emergency? This special aircraft is being used to improve plane safety under bad weather conditions. Inside the fuselage is a blind cockpit equipped with a new type of landing system. As the real plane makes its approach, the experts in the experimental cockpit must fly blind, using only what their instruments tell them to land correctly. Until now, all flyers have used the force of their muscles, multiplied by gears and motors, to adjust wing and tail surfaces. By contrast, the pilot of this experimental aircraft need only indicate the desired flight path to a computer, which then calculates and actually executes the control changes needed to stay on course. While large aircraft receive much attention, small general-purpose planes, which outnumber the world's transports by 100 to 1, are also being improved. Several recent studies are concerned with spins and stalls, the largest single factor in general aviation fatal accidents. The research objective, to provide design data for efficient light aircraft that will not stall or spin unintentionally. Even the worst eventualities are considered. Crashworthiness tests determine how to minimize impact effects. In less than a century, flight has become a part of daily life and the focus of intense scientific research. Today's priorities may change again in the future, yet flight will remain both craft and science, the technological art form of the 20th century.